Hello everyone, and welcome back to our course on using information theory to analyze complex systems. In the previous sessions of this course, we've focused on the theoretical aspects of information theory. If you'll pardon the pun, we haven't really made the connection yet to complex systems in particular. And that's something that I want to use this session to try and pivot towards. Our session is called Information Theory, Self-Organization and Complex Systems, and we're going to start to make that connection. In particular, we're going to start focusing on looking at self-organization and using information theory to quantify various aspects of that. So our outcomes for the session are for you to understand the concept of self-organization, and in particular to also understand various candidate approaches to both measure it directly at a system level, as well as various ways we can quantify different aspects of self-organization within a system. Our primary references here are one section from my book on local information dynamics, a small section there. A larger, more detailed reading is given by Prokopenko et al. For me, the best way to start thinking about self-organization is to think about examples. A good example to start with is the game of life, a canonical or classical complex system. Up in the top right corner here, we can see an image of a glider in the game of life, a self-organized structure that replicates itself over space and time. What we can do is look at the game of life on a larger scale, not just look at one glider, but look at the system level of the game of life. A good, easy way to do so is using the NetLogo agent-based modeling system. You can download this yourself and run it. I've given you some guidelines here on where to find the game of life in the models library, or you can do it directly on the NetLogo website by following this link here. Let's go and have a look at NetLogo, the NetLogo implementation of the game of life ourselves. So here it is. What we can do is we can set up a random initial condition, and then we can start running it. I'll just slow the speed down there a little. We can start running it and observe what's happening. Fairly quickly, we can see that we go from that random initial condition to something where there certainly seems to be more structure. We can see different areas in the system have already achieved some level of order. We see some static structures, some blocks here and there, some other static structures here. We can see other aspects that seem to be more chaotic or random. If we look more closely at them, there certainly is some structure in them. There certainly are some moving, coherent structures. If we look very carefully, we can probably find some gliders moving across the CA and interacting, and certainly we see lots of those interactions between the entities, sometimes creating interesting patterns. Sometimes they become static, sometimes they simply die. As time is going forward, we can see less and less of this apparent randomness and more of a static structure or organization appearing. And if we let this go for a long time, all of that will die, and we'll have static structures or periodic repeating structures called blinkers everywhere across our CA. So we've just observed this transition from a random initial state through to an intermediate state in time, where we have a mix of ordered areas and chaotic or apparently random areas with lots of interacting structures, through to a more static final state. There are a number of questions we can ask ourselves about what we've seen here in terms of self-organization. So we can try and describe these intermediate and final states in contrast to the initial random state here, as I've just done. We can then ask about whether the system organized and in what way it did. certainly I think the game of life can be considered as having organised. We've gone from an initial state without any apparent structure to it, through to an intermediate and then final states where there's much more apparent structure taking place. There are much more static, many more static structures, and even moving, spatiotemporally moving structures like the glider that we see here. In what way did it organise? Well, we know it's organised through the interactions of which cells were alive and which cells were dead, and how they produce the alive and dead states of their neighbours as time goes on. Which basically answers my next question here on how that happened. And certainly there doesn't seem to be any central control here, unless we want to think about the time switching as some kind of central control. You didn't see me going in and directing these entities in any way, or even intervening in the system at all. You can do that. You can look at that NetLogo model. You can actually turn on intervening in the system and try and see what happens, and that gives you some very interesting results. But in this particular case that we just looked at, the organisation happened without any central control from me. We can also ask about what happens to the density as we go from this random initial condition through the final condition. In this example, clearly it drops. We can also ask, does the original density matter to what kind of intermediates and final states we get? We know it matters on a detailed level. If we play around with it, you'll see that in general, over a large range of densities, it doesn't matter for the types of patterns that we get. There's a remarkable stability in the kinds of dynamics we get to the initial condition here. All of these are aspects of what we understand self-organisation to be. We can, of course, think about other examples of self-organisation, such as flocks of birds, or the way that collectors as neurons in the brain self-organise, and we can ask similar questions about those to try and get a handle on what we mean by self-organisation as well. To try and define self-organisation then, I'd like to first turn to Hiroki Sugiyama, who gives a definition that I quite like. He says that self-organisation is a dynamical process by which a system spontaneously forms non-trivial macroscopic structures and or behaviours over time. I quite like this definition. There are a couple of pieces I like here. I like the idea about talking about structure being formed, and I like the idea about this happening over time. That leads us to highlight two specific aspects or features that most more quantitative definitions of self-organisation have. Firstly, we typically see definitions talking about an increase in organisation over time. Those couple of key words that I just mentioned. We also see highlighted the feature that the dynamics are not guided by any centralised or external control agent. Now, the latter aspect there, centralised or external control agent, that's something that can be analysed separately. There's a nice paper from Niels Bertschinger and company, my former colleagues at Max Planck Leipzig, that looked at divisions between a system and external. But that's not something that we're going to get into here. And often in analysis of self-organisation, it's not really taken into account. It's either taken for granted that we're looking within a system, for example, or simply ignored. Now, I'm not saying that's the right approach. It's just what often happens. So here we're going to focus on the first part of the definition here, looking at self-organisation as an increase in organisation over time. So if we have a good way of quantifying organisation or order or structure, then we can simply look at how that changes over time, and does it seem to increase? And that can tell us whether we have self-organisation in the system. So to take that further, in our next short video, we're going to look at how we might quantify organisation or order or structure.